my name is Ali, and in this video, I'm gonna show you what I've built over the last months. It's the demonstration demo lesson that explains the Pythagorean theorem. And I would like to tell you a story, the reason why I decided to make something like this. So last year, when I was preparing for my physics exam at university, um, I realized that I need to know math. My math was not that good at that time, and I believe I didn't understand what math actually is. Um, and I started learning it. After some time, where after proving several formulas, after showing application where math was used, I realized that I've been learning math wrong since high school, actually since primary school. Um, and that realization actually encouraged me and motivated me to make something like that. It's quite probably similar to the platform that's called brilliant.org. Um, yeah, so let's get started. So Pythagorean theorem, relationships between side of the right triangle. Objective, learn what the theorem is, understand the logic behind, apply it. Prerequisites, area, right triangle, coordinate system. So the Pythagorean theorem applies only to right triangles. It states that the square of the hypotenuse, the side opposite the right angle, is equal to the sum of the square of the other two sides, legs. Divide the formula into several parts, analyze each one, and ask yourself, where have I seen this before and what is similar to? So, okay, here's the formula, and if we divide it, yeah, obviously it's the area of square. Okay, let's continue. So yes, as you might have noticed, the formula includes the area formula for square, side multiplied by side. The formula means that the area of square built on the hypotenuse is equal to the sum of the areas of the squares built on the other two sides. However, over the formula. Okay, so okay, this is, as I understand, the area of square built on the hypotenuse. This is another square, and this is another. So we have these two squares, and their the sum of these areas is equal to the area of this square. Okay, let's continue. It's quite understandable. So use the slider to change the side of squares. Zoom is available. Okay, so what we see here is like right triangle, and we see three squares. We can change their size, and we see that our formula actually works. Okay, let's continue. All right, in this section we begin our proof of the Pythagorean theorem. We'll use four identical right angled triangles to form a large square. When arranged properly, these triangles will leave a smaller square as empty space in the center. Important, make sure the triangles don't intersect with each other. Each triangle should fit perfectly without overlapping. Um, okay, obviously I know how to do that because I was the one who created um, the entire lesson. There's two ways, uh, two main ways how to do that. So one of them, it's this. So, okay, let's continue. There are two main ways to construct a square using right-angled triangles. Choose the square construction method you would like to explore next. So let's see. Okay, I have back here. Okay, so I constructed this, and this is another way to construct it. Okay, let's go with the first one. Okay, hover over the formula below to see which part of the square they represents. So total area of the big square. Okay. Area of small square. Okay. That's also understandable. We have here is B the whole side and here is A. So this side must be equal to B minus A. Okay. AB over 2 area of right triangle. Okay, and total area of four right triangle is 4 multiplied by AB over 2. Okay. Here's a visual proof of the Pythagorean theorem. The large square consists of four right triangles and smaller square in the center. In the formula, adding the areas of all four triangles and the small square gives the area of the big square. So what it means is that um, we have four right triangles and their areas. Um, if we sum up area of four right triangles and the the area of square at the center, we'll get the entire area of the big square. Okay, that's understandable. Analyze and try to understand each step. Okay, that's exactly the same. Now we just do some mathematical operation to show that the Pythagorean theorem is does actually exist. So, boom, the formula is proven. Now that we see where it comes from, let's dive into how to use it. Okay, now let's dive into application of the Pythagorean theorem. Let's say we're given with 2 points and we need to find the distance between them. Do you have any idea how to find the distance? Yeah, sure I have. Think about how you can apply the Pythagorean theorem to solve this problem. Here are a few guiding questions to help you out. What information is given? What does the Pythagorean theorem Tell us. Which shape can the Pythagorean theorem be applied to? Okay, obviously I know everything here. Yes, we need to construct the right triangle. Remember, the Pythagorean theorem can be applied only to right triangles. The question still remains, how can we find the distance? Let's remind the Pythagorean theorem, c squared, okay, is equal. The distance is hypotenuse, so we need to find c. Okay. The next question is what a and b are equal to. Try to answer before going forward. Okay, we only know the coordinates of 2 points that are given to us, only x and y's. So let's define a and b using what we know. So we see here that what a and b are equal to. Yeah, and we get the formula, the final formula. That's also called Euclidean distance, and I mention it here. It's often written as d and called the Euclidean distance. Okay, let's continue. You may wonder, why do we even need to find distances? A simple example is navigation systems. Imagine you're an Uber manager sending taxi drivers to clients. Now you need to pick the closest taxi to the client, knowing that the client location is at zero point and you have the location of all the taxis. Okay. The closest taxi is the one with the shortest distance to the client, right? So to find it, we just need to calculate all the distances between the client and the taxi, and then compare them. Research and understand the shortest path between 2 points is a straight line. Okay, yes. Let's start by calculating the distance between the client and the taxi at minus 6, 0. You might already guess that the distance is 6, but let's use the Pythagorean theorem to prove it. So it's actually kind of and intuitively understandable. It's able that um, the distance is 6. So let's continue. Okay, here we use the Euclidean distance that we derived from the Pythagorean theorem. And again, yeah, and we find that the shortest distance was 4. Okay, now let's see another way to use the Pythagorean theorem. We'll use it in classification problems where we sort things into different groups. Classification, the process of putting things into groups based on their type. For example, when you see a chair, you know it's chair because you've seen chairs before. Your brain puts it into the group called chairs. The same happens when you see a table. You recognize it and put it into the group tables. This is how classification works. We'll look at something and decide which group it belongs to. Okay? Which fruit do you think it is? Hmm, I think it's banana. Oh, I'm right. Is it banana or an eggplant? I think it's banana. Alright, take a moment to think about how you recognize a banana and told it apart from other fruits and vegetables. So I already know the answer, so I'll just continue. First, your brain quickly compared the shape of the banana with other fruits. The shape you saw was mostly like a banana's. Then you probably compared the color too, right? The eggplant is purple and the banana is yellow. Think, how can we tell the difference mathematically? Try to answer this question. How can we figure out how similar, or close, or different, or far two objects are? To compare fruits and vegetables, we need to gather information about them, just like how we, as humans, first learn what a banana is and then compare it with other fruits. What characteristics do we know about fruits and vegetables that we can collect? Their color, shape, taste, the place they grow, and so on. However, math works only with numbers, so we need to convert all the non-numerical values into numbers. Okay? Again, we need to collect information first, just like how we learn about something before comparing it. Similarly, the machine must first learn about fruits and vegetables before it can compare them. Research and understand. Information or data collection is one of steps of mathematical modeling. To keep it simple, we'll only focus on two characteristics of fruits, color and shape. We won't look at all fruits and vegetables either, just to make things easier. Okay, here we have coordinate system. Um, and as we mentioned before, math only works with numbers. So you may wonder how we can turn shapes and colors into numbers. It's actually quite simple. We can place any fruit or vegetable with a curved cylindrical shape on the left side, and as it becomes more round or spherical, we move it toward the right. For colors, we can assign a number to each color. For example, red could be 8, so we can see here 1, 2, 3, 4, 5, 6, 7, 8. So yeah, right here. And for color, yeah, so and yellow could be 0, so it's here, and so on. Okay, let's continue. Look at the coordinate system. This dot at the point 1, 1, which represent a fruit or vegetable that is cylindrical in shape and yellow in color. So it's right here. Cylindrical in shape and yellow in color. Actually, yeah, I forgot to write here curved cylindrical, but whatever. So which fruit or vegetable do you think has a cylindrical, curved cylindrical shape and is yellow? I believe it's banana. Yeah, as you might guess, that's banana. You haven't forgotten the Euclidean distance formula, right? Just like humans compare objects by looking at how close or far they are based on what they learned, the same way machines can calculate the distance between an object and a group. The shortest distance to a group means that the object likely belongs to that group. The point at 1, 1, representing cylindrical shape and yellow in color, is closest to the banana group. So it's reasonable to say that our point is banana too. Okay? Don't think of Euclidean distance as just physical distance. It's really about closeness. You can ask how close or similar is x to y, like one object to another. This idea helps in classification problems where we try to figure out what group something belongs to, like recommendation system. Yeah, I forgot to remove gaps here. Okay, this app look at what videos or posts you like before. If a new video is close to what you enjoy, same topic, style, or length, they say you might like this too. So I won't now read everything, but you can stop and read by yourself. Okay, let's continue. Euclidean distance helped us measure how similar or different things are. The closer two things are, the more likely they belong to the same group. That's it. It's just a smarter way to compare. Okay. Let's look at another example of classification. Imagine you want to predict where your classmate will go after school based on how much it wants to study and how tired it is. Okay, take a close look at the table, then continue. So here we have two parameters, desire to study and level of energy. So 0 means completely drained and no desire at all. Then 5 is neutral and 10 full of energy and motivated. Okay, let's continue. Let's say you've been asking your classmate about its desire to study, energy level, and where it's going after school for 28 days. You will notice that we have 28 points on the coordinate system, with each point representing one day. Okay, yes, here we see 28 points. So all points are not presented here. It's done intentionally to save space. So, I mean, here I didn't show the entire list. So take a look at the table and the coordinate system. Try to find some groups. Think to yourself, if I don't have energy and I don't want to study, then. So if I don't have energy, so it must be somewhere here. If my energy level is low and I don't want it to study, so it must be like somewhere here. And we see here that there's a group. Um, yeah, and place probably it will be home. It will be home actually. So you might notice that when your classmate has low energy and a low desire to study, it usually goes to home. Yeah, this is red group. That makes sense, right? Right. Okay, you might notice as well that when your classmate has energy and a low desire to study, it usually goes outside, maybe hang out with friends or play football. That also makes sense. Yes. See, like here is a group. Okay, let's continue. The situation is different when your classmate has a lot of energy and a strong desire to study. It goes to the library. Yeah, fair enough. The last group we see is when your classmate really wants to study but doesn't have much energy. It usually goes to a park with a book. Okay, the last group. After collecting data for 28 days, let's say you now want to predict where your classmate will go after school. To figure it out, you just need to know two things: how tired it is and how strong its desire to study. So then you just turn its answer into numbers and plot them on the coordinate system. Okay, and so we have here one dot appeared. Uh, as you could understand, we'll use Euclidean distance to find the group uh, to the to find the group the point belongs to. It's most likely to be this green group. Yes. So in this case, the point falls into the library group, so that's where the classmate will go. Okay. Let's see another example. Again, we need to calculate the distance. In this case, it turns out that the classmate will go to the park. Okay, so that's the end of my demonstration. I know that uh, I need to actually work and fix some bugs, probably add more problems, more quizzes, um, and I will do it, and soon I will release it. So thank you for your attention. Thank you for watching this video. Yeah. Bye bye.